All right, people. Hello. All right, keep looking at Pika because Pika's the star of the show. All right, so let's check this out. Pika, don't be shy. There we go. I don't wanna ruin things. Okay. So let's check this out. So, oh, I don't like that 3. Let me fix this. You know what? I done goofed. I forgot what problem that was. That was 118. Alright. No, not 118. Hello. Oh, 112. There we go. So all of that just for that subscript. Can you believe that? Like sometimes I am super lazy with things. Oh, I'm sorry, Pika. Did I startle you? I apologize. All right. So methanol is also called methyl alcohol. It is the simplest alcohol. It is used in fuel race cars and is a potential replacement for gasoline. Actually, this thing is crazy. If you didn't know, methanol can produce invisible flames. So if you ever look at like some Formula One racing or NASCAR racing or any type of racing where they use methanol in race cars, and you see some guy running around frantically after being in a car crash, it's because he's on fire. We just can't see it. Also, methanol is crazy. A bunch of people went blind for drinking it during the Prohibition era in the 1920s. Look into that. That's kind of interesting too. All right. So methanol can be manufactured by combining gaseous carbon monoxide, and hydrogen. So it seems like carbon monoxide, it says gas, plus hydrogen, so that's H2 gas, can be used to make CH3OH. And then this is an alcohol. So this, let's just say it's a liquid. All right. So let's check this out now. Inside this formula, well, there's 1 carbon, 1 oxygen, 4 hydrogens. So all we got to do is put a 2 here to balance in. Boom. Look at that. Balanced chemical equation. Now, it says suppose we have 68.5 kilograms of CO and it is reacted with 8.60 kilograms of H2. So we have a little bit of work to do. They're asking calculate theoretical yield of methanol. So we want to find out how many grams of CH3OH we can make using these substances. We don't know which one's going to run out first. We always have to take that into account. So let's do a limiting reactant style problem. I don't like working in kilograms, but I know that 1 kilogram is the same thing as 1,000 grams. I know that 1 kilogram is the same thing as 1,000 grams, okay? And I know that's grams of H2, so I'm going to put grams of H2 at the bottom. And then over here, I know it's grams of CO, and we want to go to moles of CO. Over here, we want to go to moles of H2. Now, luckily, I just recorded that other video, so I know this is still 12.02. Now, carbon is 12.01, oxygen is 16, so that's 28.01 grams. All right, now we're at moles of CO, moles of H2, but we don't want that. We want CH3OH. We want this. So what we need to do is we got to use the mole ratio. The mole ratio, and we use that from the balanced chemical equation. Luckily, we already balanced it. So this is a 1-to-1 ratio, so we just put 1 mole of CO equal to 1 mole of CH3OH. Over here, we got 2 moles of H2, and this is for every 1 mole of methanol, CH3OH. Let's check it out. If you ever hear like ethanol, methanol, propanol, pentanol, all of that has to do with the number of carbons. Methanol is 1 carbon, ethanol is 2 carbons, propanol is 3 carbons, and you'll learn more about that in OChem. But just a little side note. Now, we don't want moles, right? So we get rid of moles. So moles goes at the bottom. We want grams. We want grams of methanol. Now, how do we get grams of methanol? Well, carbon is 12.01. All right, so we know that one. We know hydrogen is 16. So far it's 28.01 grams. And we got to add 4.04. So that's 32.05 grams. 32.05 grams. All right, so you don't need a calculator all the time. Remember your most common compounds. Let me, oh, hello, Bika, give me 1 second. So this seems like a lot. But it is. So just deal with it. No, Pika, come back. Don't leave me. Not mid-video, Pika. You're going to ruin the video. Don't leave me. Aw, peace out, fool. My life. It serves no meaning anymore. Pika, come back! Alright, whatever. I won't cry. You'll cry. Alright. Alright, whatever. Let's do some math. All right. 68.5 times 1,000 divided by 28.01. And then we're ignoring the ones. Multiply by 32.05. And this right here can make a bunch of, it makes 78,000. 78,400. We're rounding 78,400 grams of CH3OH. Why are we rounding? We only have 3 significant figures, so we can only write 3 significant figures there, okay? Keep that in mind. All right, so let's do that with the other one. So we have 8.60 multiplied by 1,000, so we can turn it into grams. Let's divide by 2.02. Let's divide by that 2. And then let's multiply by 32.05. In this one, again, we only have 3 significant figures, so it becomes 68,200 grams of methanol. So we have whichever one's running out first. This is the lower number, so that's our limiting reactant. This is what's going to run out first. All right, and this is what we're actually going to make. All right. So, no, that's what we can make. That is our theoretical. Whenever you do a calculation of limiting reactant, you calculate what's called your theoretical yield, what you should make if nothing goes wrong. If you don't contaminate, if there's no spills, if nothing evaporates on you, if your glassware isn't contaminated, if everything goes beautifully, that's what you should make, your theoretical. All right, so that's called your theoretical yield. Now your theoretical yield should always be compared to what you actually make. So your percent yield is equal to what you actually made divided by what you could have made or what you should have made. So we should have made 68,200 grams, But over here, it tells us we made 3.57 times 10 to the fourth grams. All right. And then what we're going to do, since we want a percentage, we multiply by 100. So let's check that out. Now, 3.57 times 10 to the fourth, that means we're moving the decimal places 4 times, which is going to be, it brings it up to 35,700. And we divide that by 68,200. We multiply by 100, and we get 52.3, because we only have 3 sig figs, 52.3% yield. So what that tells us is that in our chemical process, in this process to create methanol, they only made 52.3% of what they should have made. Now, in your mind, you might be thinking, well, that should be 100. That should be 100. Why isn't it 100? In reality, most chemical processes do not reach 100. Some of them do. Some of them get really, really close. But when you start talking about like organic chemistry and making all these like other substances, like sometimes your percent yield is like 2%, 1%. It gets crazy. But some reactions are very, very, very efficient, and you can get really, really close. All right, so this is how you calculate percent yield. You do your limiting reactant, you find out which value is the lowest, that's your theoretical yield, that's what goes at the bottom, and then the problem should give you what you actually made. If you do this in a lab, this is your experimental value. All right, I would write that down on your notes somewhere. You would put that as your experimental value, and you're going to have a lab where you have to do that. All right, in every lab where you make something, you're going to have to calculate this, so do not forget that. All right, because that's where a lot of the points are going to come from. But that's basically it. You get your limiting reactant, whichever one's the lowest value is how much you can actually make, or how much you should make. That goes at the bottom. What you actually made through an experiment goes at the top. All right, so you got a few of these problems. You got a decent amount of these problems, okay? All right, and that's, am I missing anything? Percent yield, I'm missing one type of problem. I got to go back and add that. But anyways, that's it. People, peace out.